Hello, complex students. So today we're going to talk about how antiderivatives relate to contour integrals. So first of all, let's specify what we mean by an antiderivative. It's the same as it meant in calculus, though. We say big f of z is an antiderivative of little f of z on some domain D if the derivative of big F is equal to little f for all z in the domain. Here's the big theorem that we're going to work with in this lecture. So first, suppose that the function little f is continuous on your domain D. So the following three things are all equivalent to one another. The first, part A, is that little f has an antiderivative, big F, on the domain D. The second part is that if you look at any integral of f along a contour inside of D that goes from z1 to z2, all of those integrals have the same value. In particular, you see that the value of the integral is just the antiderivative evaluated at z2 minus the antiderivative evaluated at z1. So it looks like a fundamental theorem of calculus. So what this is saying is that contour integrals inside of D are independent of the particular path that you choose. All that matters are the endpoints. So a function having an antiderivative means the same thing as having independence of path in terms of evaluating contour integrals inside that domain. And the last part is that if you look at any closed contour inside of D, the integral around C of the function little f will be 0. So all of these things are equivalent to one another. Existence of antiderivatives, independence of path, and integrals around closed contours are 0. All mean the same thing logically. So before we try to prove this theorem, which is a bit involved, especially one particular part of it, let's do a few examples to see kind of how we can utilize it. So in the first example here, we want to integrate 1 over z squared, where c is the top half of the unit circle. Let's observe that big F of z equals negative 1 over z is an antiderivative of little f equals 1 over z squared on the domain c minus the origin. And also our contour c, which is the top half of the circle, is contained in that domain. Well, the fact that we have an antiderivative for the integrand on a domain and the arc that we're integrating along is contained in that domain, then it tells us that our integral can be evaluated just by doing that sort of fundamental theorem of calculus-like formula. So you take the antiderivative, negative 1 over z, and you evaluate it at the endpoints of the arc. Now the endpoints of the arc here, this is the top half of the unit circle, so the terminal point is negative 1 and the initial point is positive 1, and you end up with 1. When you plug in negative 1, then you'd get plus, because you do minus negative 1 over z. Then you plug in 1 and you get 1 again, so the final result would be 2. On the other hand, in the next example, we have the same integrand, but we have a different curve this time. This time we'd be looking at the full circle. It has the same parameterization, z of t equals e to the it, but the parameter t runs from 0 to 2 pi in this example, so it's forming a full circle. So that's a closed curve in that same domain. So it's C is a closed contour in that domain D equals the complex plane minus 0, where little f of z equals 1 over z squared has antiderivative big F of z equals negative 1 over z. So the previous theorem tells us that the integral around this curve is 0. I could confirm it by doing plugging the parameterization into the curve and actually working out, the integral in terms of the definition of contour integral, but it's unnecessary. The theorem guarantees it. We'll get 0. In the next example, we're going to try to integrate the function 1 over z along the curve c1, where c1 is the semicircle that's the right-hand side of the unit circle. And so we have a parameterization for that over here. It's just your standard parameterization where t ranges from negative pi over 2 to positive pi over 2. Well, here let's consider the principal branch of the logarithm capital Log, we know that the derivative of the principal branch of the logarithm equals 1 over z on the domain. At the right, I've drawn a picture of what the domain of the principal log looks like, but just you remember you take the branch cut along the angle negative pi, so it'd be c minus the set of points of the form re to the I pi, where r is greater than equals 0. So we're just taking that ray at the angle of pi, and we know that also on that domain, let's call this d here. On that domain, well, we know how the principal log is defined. You just always take the angles between strictly greater than negative pi, less than or equal to, or strictly less than positive pi. Okay, so point is we have an antiderivative on this domain, and we know that our curve C1 is contained in this domain of the principal logarithm. So since our integrand has an antiderivative of the principal log on this domain, and our curve is contained in that domain, then by our previous theorem, integral C1 1 over z dz will equal the antiderivative evaluated on the endpoints of the curve. So you put the initial point at the bottom, negative I, and then positive I at the top. So that will be log I minus log negative I, using principal values here. And log I, you do natural log of the modulus, which is 1, so you just get 0 there, plus I times the argument of I. Well, if we're restricting between negative pi and positive pi, the argument would be pi over 2, minus, then you do natural log of the modulus of negative I, which is also 1, plus, and then we do I times the argument for negative I, which would be negative pi over 2, if we're using principal logarithm, for a grand total of I times pi. But now let's change the situation up. In the next example, I'm integrating the same function, but now my arc is the right-hand side of the semicircle. And the parameterization I'm giving has the parameter running from pi over 2 to 3 pi over 2. So you can see that if we tried to use the principal branch of the logarithm, which has its branch cut along the negative real axis, that branch cut would intersect this curve, and so our curve would not be contained in the region where we have the antiderivative. So we have to just work with a different branch now. So let's consider the branch of log z, where log z is equal to, natural log of the modulus of z plus I arg z, where we restrict the arg to be in the interval from 0 to 2 pi. So what I'm doing here is I'm putting the branch cut along the positive x-axis. So we know that the derivative of this branch of log z is equal to 1 over z. Previously we proved that the derivative of any branch of the logarithm is 1 over z. And that's true on this domain d equals the complex plane minus the set of re I times 0, r greater than or equal to 0. In other words, the non-negative real axis. And we have our curve C2 is contained in that domain. So we have an antiderivative of the integrand on a domain that contains our curve. So our curve is not going through the branch cut. And so now we can do the integral along C2 of 1 over z, and that'll just be our antiderivative log z, where we understand what branch we're working on here. And from the limits of integration will be I on the bottom and then negative I on the top. And then you plug in those limits of integration. And similar to how we did the computation before, in both of these endpoints, the modulus is 1, so the natural log part is 0. So we're just going to get I times the argument of negative I. But now we're picking our angle between 0 and 2 pi. So for negative I, we're going to get 3 pi over 2 for our argument, minus, and then when we plug in I, the argument is going to be positive pi over 2. So you end up with, I times pi. Cool. So we're able to do that just by working around, picking a branch cut that doesn't intersect our curve. One cool thing is that, so one thing that we can't do with the theorem that we're currently playing with is we could never have integrated all the way around the unit circle, because any branch cut of or any branch of the logarithm, its branch cut would pierce the circle somewhere. But we have done the right half and the left half. So we had a previous result that said, hey, if you wanted to integrate all the way around that unit circle, call that C, then that could be done by integrating around C1, 1 over Z, plus C2, 1 over Z. And we just calculated both of those integrals, and we got I pi for both of those answers. So interestingly, we can integrate all the way around that circle, 1 over Z, and we get 2I times pi. Notice that we integrated around a closed contour, and we did not get 0, because the function 1 over Z does not have an antiderivative that contains the entire unit circle. Any antiderivative of 1 over Z would be missing one point on that circle because of the branch cut involved. So you don't always get 0 when you integrate around a closed loop. Sometimes you get non-zero answers, and it usually has to do with, there's some sort of problem that the curve is encountering along the way as you go around with a discontinuity of the function. Okay, so let's prove the theorem. So the way we're going to prove the theorem that had the 3 parts that were equivalent, we're going to prove them in a cycle like this. A implies B, which in turn implies C, which implies A. So if you can prove those 3 things, 1, 2, 3, you prove that all of those conditions are equivalent because they all imply each other, right? So A implies B, but then you see that B implies C implies A, so B implies A, so A and B imply each other. So everything's on a circle here, right? So anyway, so A is the statement that the function little f has an antiderivative big F in the domain, and part B is that contour integrals are independent of path in that domain. So let's suppose little f of Z has antiderivative big F of Z on our domain D. And for now we're going to take C to be not just any old contour, but we want it to be a smooth arc. Let C be a smooth arc. All a contour, remember, a contour is a piecewise smooth arc. So you get a contour by just stitching together a bunch of smooth arcs. But it'll be easier to first prove the result for a smooth arc, and then stitching together several of them will be pretty easy. So we start with a smooth arc from, what we want to say, inside D, from Z1 in D to Z2 in D, having parametrization Z of T, where T ranges from A to B. One of your homework problems was to prove that the derivative with respect to T of a function that's differentiable on a domain containing Z of T, the derivative of this composition just basically follows what you would expect for a chain rule. It's big F prime of Z of T times Z prime of T. So that was your homework problem. And since we're saying big F is an antiderivative of little f, this is the same thing as little f of Z of T times Z prime of T. Now thus, here's how we can use that. If we want to integrate along C of little f of Z dz, well, we basically have an antiderivative for that composition now. See, this by definition is the integral from A to B of little f of Z of T times Z prime of T dt. This is just the definition of contour integral. But we know that this just works out to be big F of Z of B minus big F of Z of A, because of this fact in yellow here. So notice that, this is just doing big F of Z evaluated from Z1 to Z2. Z1 was Z of B, right? And Z2 is Z of B, and Z1 is Z of A for this particular parameterization. So now we can adapt this to work for any contour. Now if C is any contour, we have C is equal to like C1 plus C2, some finite sum of smooth arcs. So that tells me that if I want to do the integral over C of F, that's the same as doing the integral over C1 plus C2 all the way up to Cn of F, which we know we can break up into a sum of integrals. And then, you just end up with this telescoping sum. Like the first one's going to be, like let's say that, let me squeeze something in here. And let's say that Ci goes from Zi to Zi plus 1. So this sum of integrals that you'll get by our previous result will just be like big F of Z2 minus big F of Z1 plus, then you'd get big F of Z3 minus big F of Z2 plus all the way down the line. The last one you'd get would be big F of Zn plus 1 minus big F of Zn. And when you analyze all the terms that cancel off, you're only left with the last one and the first one. So you end up with big F of Zn plus 1 minus big F of Z1. And you see that the curve C goes from Z1 to Zn plus 1. So you're getting the antiderivative just by evaluating on the endpoints again. So the same result holds even when you're doing a smooth contour, which is just a sum of a bunch of smooth arcs. All right, so that proves the A implies B part. Okay, to prove B implies C, we have to prove that if the domain, or if the integral has the quality of independence of path, then the integral around any closed curve will have to be 0. So let's suppose that we have the independence of path. Now let's let C be a closed path, or a closed contour in D with, let's just say Z1 and Z2 just being two arbitrary points on C, not equal to one another. So our hypothesis would say, if we do any integral from Z1 to Z2, so here's my contour, and I picked a point here Z1, and I picked some other point Z2 on it. So, I mean, essentially what we can do is just pick that part of the contour that goes from Z1 to Z2 along the closed loop C, but I could also do Z1 to Z2 working backwards along C, going the other way, going around the other half of the curve. So we'll do something like make this top part of C here be C1, and then the bottom part of C here from Z1 to Z2 will be C2. So form C1 and C2 from Z1 to Z2 so that C is equal to C1, and then you do minus C2, like go backwards along C2. So then the integral along this closed curve of F would be the integral along C1 minus C2 of F, which we know we can break up into integral C1 along F minus the integral along C2 of F. But C1 and C2 are both paths from Z1 to Z2, and we have independence of path, so these two integrals are equal by hypothesis. So that means that this has to be equal to 0, which proves what we wanted, that the integral around any closed contour has to be 0. Okay, lastly, we prove the hard direction, C to A. So we want to prove that if all integrals around closed contours inside of the domain are equal to 0, then the function little f has an antiderivative in that domain. So suppose integral around C of little f of z dz equals 0 for every closed contour C contained in D. So the first thing we're going to do is show that integration of the function f is path independent in D. So just let C1 and C2 contained in D be any two contours from some fixed point Z1 in D to some other fixed point Z2 in D. And then we're going to just let C equal C1 minus C2. Well, if you do that, you know, here's Z1 and here's Z2. You made one path, here's C1, and you made some other path, C2. So if you do C1 minus C2, it just forms the closed loop going from Z1 to Z1. So C is a closed loop, or a closed contour. And by hypothesis, we know that the integral around that's going to be 0. And then that tells us that the integral around C1 minus C2 of f is equal to 0, which we quickly deduced that the integral around C1 of f would be integral around f of C2. So that's independence of path right there, right? Any two paths, C1 and C2, from Z1 to Z2 had the same integral. So it's important that we have independence of path, because now we can define a function. So we're going to define, this is going to be the antiderivative of little f. We're going to define big F of s to be the integral from Z0 to Z of little f of s ds. And just note, big F is well defined. In other words, it's a single valued function because of independence of path. I guess I should have said here when I'm defining that function that little s would be contained in D, and so is Z naught. So S and Z naught are in D here, of course. So we have independence of path inside of D, and so Z naught, think of as a fixed point, and S is like your variable. So, you know, it doesn't matter what path you choose to go from Z naught to Z. Oh, I should say Z is that should have been f of Z, rather. F of Z. F is just S is just a dummy variable that you need inside the integral, but Z is the variable of our function. So what we want to show is that big F prime of Z is equal to little f of Z. Well, let's break that down. So at this point, we don't know anything about big F other than, you know, we could, if we want to take its derivative, we could use the definition of derivative. So let's just see what happens when we try to do that. So big F prime of Z, by definition, is the limit as delta Z goes to 0 of big F of Z plus delta Z minus big F of Z over delta Z, which is the limit as delta Z goes to 0, 1 over delta Z times, then we've got that big F of Z plus delta Z would be the integral from Z naught to Z plus delta Z of F of S ds. Then we do minus, then we do the integral from Z naught to Z of F of S ds. Now, one thing that we need to understand about that delta Z is that it has to be sufficiently small so that Z plus delta Z stays inside our domain. So we want to examine, if we look at this difference of integrals here, if you think about it, I mean, you got Z naught here, and then here's Z, and then here's Z plus delta Z, and we have independence of path, right? And so because we have independence of path, we know that the first integral here that goes along the first jog of this curve, it only depends on what happens at Z naught and Z, but then the second one, you'd get the same result, what happens at Z, you know, minus what happens at Z plus delta Z. So the part that happens in the middle here is just sort of going to cancel off, and this will reduce down to limit as delta Z goes to 0 of 1 over delta Z, and the only endpoints that matter are Z naught and then Z plus delta Z. Oops, sorry, we're taking the difference here. So the part in the middle is the part that's going to cancel off, and you'll be left with just, no, I keep saying that wrong. You just end up with, see, we're taking the whole thing minus the shorter thing, and so we're just left with this much of it. So that'll be Z to Z plus delta Z of F of S ds. So we're wanting to show that this limit here, what we want to show, we want this equal to F of S, or F of Z, rather. So if you want to show that that limit equals F of Z, you got to show that the difference between the thing you're taking the limit of here, I need to show that the difference between this and this gets arbitrarily small. So this is the difference here in blue that we need to examine and show that, okay, that gets arbitrarily close to 0. So the trick is going to be is we're going to look at the F of Z here, and we're going to show that we can express that as an integral so that we can combine it with that other integral, and we'll get something that we can get a handle on because we know that our function little f is continuous on this domain. So let's do that. So observe that if you do integral from Z to Z plus delta Z of just ds, so you're just integrating, the integrand is 1, that equals, well, you know, the antiderivative is 1, so you'd get 1 evaluated from Z to Z plus delta Z. So that's Z plus delta Z minus Z. So you just end up with delta Z. So another way to express delta Z is that's this integral over here. And then from there, you can get that if you put F of Z here, if you integrate F of Z ds from Z to Z plus delta Z, well, F of Z here inside this integral is a constant with respect to the variable S. So I can pull it out. And then this integral, we just pointed out, is really delta Z, right? So this is F of Z times delta Z. So where I'm going with this is that if I do 1 over delta Z, the integral Z to Z plus delta Z, of f of z ds, well, that'll just equal f of z. Okay, so now that difference quotient that I was kind of interested in from the beginning, the big F of z plus delta z minus big F of z over delta z, if I take the difference between that and little f of z, well, we showed that the difference quotient here in yellow a minute ago, we had that worked out to be the integral, let's just write it this way, 1 over delta z times the integral from z to z plus delta z of f of s ds. That's what we had worked out on the previous page. Minus, so this, let me color code this here. The things in yellow are equal. Minus f of z here, we just above worked out that that can be expressed as the integral from z to z plus delta z of f of z ds. And that was multiplied times 1 over delta z also, so 1 over delta z there. So the things in blue are equal, and then by properties of integrals we can combine the stuff on the yellow and the blue terms we can combine into one integral and write that as 1 over delta z integral of f of s minus f of z dz z to z plus delta z. And so now we're at the part where the punchline is getting ready to come. You see, our integrand at this point is the difference between f of s and f of z, and we know that our function f is continuous on this domain. So that means that we can make f of z as close to f of s as we like simply by, there should be a ds there, simply by choosing z close to s, right? So let's whip out the definition of continuity on this thing. F is continuous at z in d there. So for every epsilon greater than 0, there exists a delta greater than 0, such that for every s in d, if the modulus of s minus z is less than delta, it implies that the difference between f of s and f of z is less than epsilon. Thus, if we have our delta z less than delta in modulus, we have that the difference between this big f of z plus delta z minus big f of z all over delta z minus little f of z, which we know is the same as the modulus of this integral 1 over delta z, integral z to z plus delta z of f of s minus f of z ds, so all that in modulus. We had a lemma that we proved recently. It says you can pull, it'll be less than or equal to if you pull the modulus inside there. So you'd get 1 over delta z in modulus, integral z to z plus delta z, modulus of f of s minus f of z dz. So remember, delta z is just, the modulus of that is just how close z is to, like how close these points are to one another. So since we're integrating along that arc, that, you know, f of s minus f of z, they're within delta z of one another. So what's inside the integral there is less than or equal to, you know, the upper bound on the integrand, which we know it can't be bigger than epsilon, and then the length of the curve. Well, the curve is just going from the, you know, it's a straight line from one endpoint to the other, and so that'll be modulus delta z. So this just works out to be epsilon. So you see what we showed, whenever z was close to z plus delta z, in other words, delta z is going to 0 in modulus, that the difference between the difference quotient and f of z becomes minute. We get, it's less than epsilon. So that tells me that when I take the limit, that's delta z goes to 0 of f of z plus delta z minus big F of z over delta z, I get little f of z. So i.e. big F prime of z equals little f of z when z is in D. And that finishes the proof. Okay, I will stop there. Talk to you again soon. Bye.